Good morning to everybody. I'd like to welcome you back to week 3 of oceanography. It's a pleasure to see all of you on video and start a new week off with you. We are going to pick up where we left off last lesson. Last lesson, we were discussing the theory of plate tectonics. And I'd like to throw up a plate tectonic map for us to have a look at. So here is a map of the major plates. The major plates are right there. You can see a couple of things. First off, when we have we have the prime meridian right here. So the map is not centered. The map is not centered. When you take latitude and longitude readings on maps, charts, somebody that was just admitted forgot to hit the mute button. I'm not sure who it is, but if you would be so kind as to hit mute, that would help. So here's the prime meridian. When we do our maps and we talked about cartography, we say that this was agreed on internationally, and you notice it's not centered. Most here we center the Pacific plate. When you look at a map made, say, in North America, North America is usually centered. The United States, Europe, they usually center themselves. So when you take latitude and longitude readings, you learn the compass directions. West and east is WE, but that's of the prime meridian. So the Western hemisphere is from 180, right where the cursor is, all the way over to the prime meridian. And then the Eastern hemisphere actually runs around on this map. So your Eastern readings are actually in the Western half of the map. So when you take latitude and longitude, generally, most maps are centered at the equator. So your latitude's easy, north or south from the equator. But when you look at your longitude, it's from the prime meridian. Also, a couple of other little things about when you read a map, there's distortion. There's always distortion because it comes from a circle that has been cut, spread onto a flat surface, and then turned to a square. So there's map distortion. Notice how close these degrees of latitude are near the equator and how far they are near the poles. And when you look at latitude, they're called parallels because they're always exactly apart. So that is an illusion because you're taking a three-dimensional sphere and flattening it. So things near the poles tend to look bigger. So here, Greenland, you would take Greenland, and if you wanted to throw it down over America, you can see Greenland is near the size of the United States, and that's just not true. So there's always some map distortion. But that's not really what we're looking at now. I just wanted to point that out to you, that when you do map reading exercises or take latitude and longitude, make sure you find your references, the equator and prime meridian, that's where they're measured from, and then use your north, south from the equator, east, and then west from the prime meridian. But be wary, it's not always obvious when you're on a map because they do shift the view. Now, what we're looking at today is the plate tectonics. Going down to the key right here. The key, see, I wanted to make it larger, but I'll shrink it down and pull it out here. You can see this this arrow here, that's showing you the direction the plate is moving. Then you're given the 3 types of plate boundaries: the transform plate boundary, the divergent, and the convergent. Today in class, that we will be looking at that. We will definitely be looking at that. We will be looking at these 3. Transform, they slide by each other. Divergent, we're spreading apart. Convergent means coming together. When you come together, one gets pushed under the other. In this map, you can see the subducting plate is sliding under the overriding plate, and they have these blocks showing you which direction. Then you have uncertain or complex boundaries, and then the hot spots. And those hot spots are the mantle plumes that we talked about. So let's just have a look at what we have here. We'll look at the Nazca plate, which is a little fragment broken off. Notice these plates, they have consistent boundaries, but they're a little bit jagged. That's because different rocks and minerals will have different friction or different spreading points. So they don't all spread at the exact same speed. That's why you have the faults, broken faults. But let's see this Nazca plate. You can see it's sliding under the South America plate. So the overriding plate is South America. The subducting, which means going under, plate is the Nazca. You have an ocean trench. Ocean trenches are the deepest points of the ocean. We learned Mariana Trench is the deepest over here. But you have an ocean trench. That's where your subducting plate is sliding under your overriding plate, which gives you very deep. And then on the coastline, because you have subducting, you also have some uplift. You have your coastal mountains, in this case, the Andes. So plate tectonics, these subducting or convergent boundaries, they all kind of have the same features. You have a subducting plate, an overriding plate, a trench, and then an uplift. Here, Mariana's Trench, look, you have your subducting plate, your overriding plate, your trench, and then the Philippines would be those uplifted volcanic islands. In Japan, you have your subducting plate, your overriding plate, your island arc, your trench. In the Aleutians, here you have subducting, overriding. Here, Caribbean, subducting, overriding, island arc, volcanic islands. So the divergent boundaries, they are the site of destruction of plates, plate destruction. This plate that's underriding, that's subducting, melts into the mantle. Now let's look at the next type of boundary, the divergent boundary. They're spreading. Notice they're spreading here. The spreading creates new ocean floor. So you have new ocean floor spreading. You're creating at the same rate you're destroying, so the net is 0. Here on land, you do have that rift we talked about. There's the East African Rift Valley. Now this little piece of Africa is separating from this piece. You can see here, your Red Sea is part of this rift. So the Red Sea is forming, and this land is being pulled in one direction. This land is being pulled in the other direction. You also have hotspots. Hotspots are those plumes. Some are near faults, like Galapagos, Iceland. Some are far away from faults, like Hawaii, Tasmania. Some are on plates, and that would be a supervolcano because this thick granite is the explosive type. So these don't erupt very often, but when they do, they're a doozy. These are constantly erupting, building these chains of islands. constantly erupting, building chains of islands. So your last boundary, the transform, they're sliding by each other. You can see here, they're sliding by each other. So a map like this, we have one in our PowerPoints, shows you various hotspots, shows you the different types of plate boundaries and what's forming there. This is a unique plate boundary because notice it's continent to continent collision. And that doesn't happen very often, but right here, you have the Tibetan Plateau and the Himalayas, the highest point on the planet. Now, that wasn't always continent to continent, that's sutured. So there was water there. You can actually find fossils of sea life up here on the vast altitudes. So this map here, shows you a lot of what's going on our planet. Notice down here, you have the Sandwich Trench and a little bit. This is the only active plate margin in the Southern Ocean. Notice up here, you don't have any plate margins on the northern, in the Arctic, I apologize. Notice our coast, quiet. See this nice quiet, wide continental shelf, a lot of deposition, not much going on here. This coast, the West Coast, the Pacific type margin, no continental shelves, and a lot of plate tectonics. This little plate's interesting, the Juan de Fuca plate, which is almost totally gone. That's our Cascade Mountain range. Mount St Helens, which erupted in 1980, was a large eruption in our Cascade Mountains. The largest or the highest in the continental US, Mount Rainier, is formed here. So this Cascade Mountain range, this little plate's almost gone. You can see it's not much left of it, but it's still subducting. And you have your little trench out here. You have a little mountain range, the Cascades of volcanic mountains. So you have three very typical scenarios going on. You have your spreading, which has fissure type volcanoes, which fissure means crack. Generally, they erupt lava, non-explosive. You have your subduction, which are more violent boundaries. They grow volcanic island arcs and deep sea trenches. They replenish the mantle. And then you have these transforms where two plates are sliding by each other. You know that this is a very active earthquake zone, but you don't see a lot of volcanoes. So the plates are sliding by. You're not creating crust. You're not destroying crust. You're just moving crust. So those are our three types of plate boundaries, the different hotspots, these mantle upwelling areas. And are there any questions regarding the major plates or the dynamics of the major plates at this time? Okay.
Could you go over the uncertain boundary again?
Well, uncertain have not taken the shape yet. There's disturbances going on there, but they haven't either made the clean break into being a spread, or you don't have active subduction going on there. They're just a seismically active area that show evidence of change.
Okay, thank you.
No, you're more than welcome.
Question, Professor. Is
Yes,
this chart published in the textbook on a certain page? I couldn't find
I just
it.
pulled this off the internet this morning because I thought it was pretty darn good and it would help me explain. So I'll be happy to attach it. And I mean, right now it's part of the record because we have it on the Zoom, but I'll be happy to attach a copy of it in the next review for the quiz. So you have
Thank you.
a printable one.
Thanks a lot.
Oh, no problem. No problem at all. So let's just have a look at the next lesson. We're going to continue with that PowerPoint that we were working on last class. We left off here. Notice this is, oh gosh, it's quite the same as what we had there as far as this is the seismic activity for a 10-year planet or 10-year amount. And you can see they follow our plate boundaries. There's that little Nazca plate. Here's your Himalaya mountains where subduction's occurring. You have deep volcanoes. That's where the plate is melting. You have little shallower ones. That's where it's being bent under. You have your transform boundary. More deep, notice the deeper volcanoes are subduction, where a plate is diving. The shallow ones are right there, where it's spreading. So this is our major earthquakes, the seismic activity worldwide. And we do have a few hot spots. We have an interesting little hot spot here. You know, there's our Yellowstone hot spot right there. A few random across, very rare random across the United States. So this was used as an evidence of plate tectonics for many, many years. We did touch upon this map, which is very similar to the other one. I'll use the other one in the review. We did touch upon this one at the end of last class. I am going to make it a little bit bigger here, just so we can do a quick review. It is available in the PowerPoint. You are able to download these PowerPoints and do this as well. But you can see there's your little Himalaya. That's your subduction, land to land. Here's the Philippine plate and the Pacific plate. Similar subduction where you have the little arrows pointing. These are the subducting plate. This is the overriding plate. There's your Andes Mountains. Here's the little Cascade Mountain Range. Here's the Aleutian with the Aleutian Trench. Here's your hot spot. There's the Yellowstone hot spot, which is that super volcano. So this is just a colorized, maybe a little less details on in the legend, but it pretty much follows the opener that we looked at, that I downloaded. So this is part of our PowerPoint notes here. This pretty much sums up plate tectonics. Now let's visit some of these faults and learn about them. Here's Iceland. Iceland, notice we have two plates here. So Iceland right up here, you have the Eurasian plate and the North American plate, and they meet right up here at Iceland. So here's Iceland. Here's one plate. There's your fault. There's the other plate. That is an active volcano. So you do have volcanism. And of course, it is attached to the ocean. So these fissures do fill up with seawater as well. So that's a fault line through Iceland. This is a spreading plate. It is part of the oceanic ridge. Convergent, spreading apart. Our Iceland plate is convergent, or sorry, divergent. Convergent means come together, divergent, spreading apart, transform side to side. We'll start off by looking at a divergent plate. This, taken from a textbook, here's an early stage on land rift forming. Your mantle plume causing a volcanic seam. In this case, this is how they believe Pangaea, those all lands broke apart. This is currently occurring in Africa. Kilimanjaro would have formed this way. Given a little time, you can see the rift forms. Okay, this is the next stage. This is A, here's B. It's spread apart a little bit. You still have your mantle plume. You still have volcanoes. And here would be a rift valley. That would be the East African Rift Valley. So you'd have warping, where you have volcanoes. You would have a valley forms as the plate pulls apart. There's your Rift Valley. Lastly, the third stage in this divergent formation would be a growing sea. At present, the Red Sea looks like this. In the past, when you're looking at Pangea, the Atlantic would have grown this way. So this is the birth, if you will, of a divergent boundary. Diverge means to spread apart. The birth of your divergent boundary occurs in 3 stages. The stages are warping, and then you have a rift valley, and then you have a embryonic sea. Not quite an ocean, because you don't have a full ridge. You don't have shelves built up. It takes a little time for it to become an ocean, but you have an embryonic basin that this one eventually became the Atlantic Ocean. This is an example of the Atlantic Ocean. This is occurring right now, all 3 stages simultaneously in Africa: Red Sea, East African Rift Valley, and then a volcanic zone. So this is how scientists believe divergence occurs. So we have seafloor spreading in that mature basin. That would be the next step after you have your ocean growing. It would move to the seafloor. This is the Atlantic, the mid-ocean ridge. Make this a little larger so we can see the image first. Okay, you can see there's your ridge, your spreading center, and old seamounts, guyotes around. These are extinct volcanoes as it spreads. This is your deep ocean floor called the abyssal floor. You can see right here along the continental margins, that's continental shelf. We talked about continental crust being granitic, and it extends, part of it is underwater. That's the continental shelf right there. Moving down, you got the continental slope. That's a very steep drop off to the deep ocean. So these oceanic ridges are divergent boundaries further along than our previous slide. This example is right through the Atlantic, but remember the Pacific, the Indian, they have spreading areas as well, and they all pretty much follow the same scenario. They create new ocean crust. When you move away from them, you have extinct pieces of ridge called seamounts, guyotes. Guyotes are flat-top seamounts. And then you finally have areas that have been eroded and all. That's the abyssal plain, the deep ocean. So our oceanic ridges, the divergent boundary. What powers these? Scientists believe it's convection currents in the mantle. Remember, convection is the form of energy transfer in a fluid where hot fluid rises, cools, and sinks. So you get these currents moving in the ocean, moving these plates around, or currents in the mantle moving these plates around. So there are different, convergent means to collide. Okay, so divergent, we're done. Convergent collides, plates push together. So you can have oceanic crust hitting continental crust. In this case, the oceanic crust is generally the subduction because it's thinner and denser, and the overriding plate would normally be continental. You can have oceanic crust colliding with oceanic crust, or you can have continental crust colliding continental crust. And this really is the Himalayas. We looked at that. That's where Everest is. Let's take a look at these scenarios. I will enlarge this one first. Okay, here is your South American plate and that Nazca plate, which is broken off of the Pacific plate. Nazca is subducting. You can see it's going under. There's your deep earthquakes that we saw, intermediate earthquakes, shallow earthquakes. You have your volcanic chain of mountains. That volcanic chain of mountains, in this case, is the Andes. Uplift because, as you're pushing down, you're also getting pushed up. Here is your deep ocean trench, side view, that little area where the plate collision occurs. Side view, top view. So typical subduction, you have a subducting plate, an overriding plate, a trench, and a volcanic island arc, or in this case, a continental volcanic arc. So here is what's happening right now and why the Andes are still growing. This is that little Juan de Fuca plate we talked about. And even another broken Gorda plate, Pacific plate, Explorer plate. Okay, this is a little shattered plate. And this shattered plate has a subduction zone. And this subduction zone, shallow earthquakes, intermediate earthquakes, deeper earthquakes. You do have a trench, a little deeper out here. You have spread center where crust is being created and the crust is being destroyed under the Cascade Volcanic Island Arc at the same rate. So again, another subduction zone is here. Now, an interesting thing is here the California current's running by and the westerly winds blow off here, so they become moisture laden and they get uplifted right here. So this area, Seattle, Portland, and this area here, there's Puget Sound, that's tectonic bay. It collapsed, formed by subduction. So there's a very deep 1,000-foot, more than 1,000 feet deep, this little shallow, or this bay, it's not shallow, it's got a narrow inlet. Puget Sound. These get rain all the time. So there's so much rain. A tectonic bay is a special type of estuary formed in these earthquake zones. San Francisco Bay is a tectonic bay. Tampa Bay is not a tectonic bay, still a bay. But so you get a lot of rain, You have volcanic activity here. These major volcanoes can be explosive from time to time, all associated with subduction. So that is ocean to land, ocean to land. Another example is ocean to ocean. This is how Japan formed. There's your island arc. You have a trench off the coast. There's your trench right there where it forms. Your volcanic islands. A marginal sea, Caribbean's a marginal sea. It's a sea between your island arc and the continent. So here is your volcanic island arc. There's subduction, subducting plate, overriding plate, earthquakes, abundant, very abundant here, very abundant. You have some back arc activity here in Japan. That is due to a hot spot that is not mandatory in a ocean to ocean collision. It just adds a little more variable in Japan. Japan's very tectonically active because you have an upwelling associated with your convergent zone. So there's a lot of tectonics happening here in Japan. So there's your island arc, your trench, and your ocean to ocean subduction. You have a marginal sea associated with the ocean to ocean. Generally you do, because it's not on a continent, so you don't get the explosive volcanoes, but you do have a sea between the continent and the plate tectonics. looking at the depth of earthquakes, the shallow, intermediate, deep. Again, shallow, where the subduction is occurring, but that plate's being pushed down and melting, and every time it moves, it gives you an earthquake. So earthquake depth, the deep earthquakes occur in subduction zones. Here's another image of the Peru-Chile Trench, how trenches form. You can see these are the deepest areas in the ocean. Marianas or the Challenger Deep being the deepest, but these trenches are the deepest ocean places. And you do have earthquakes on them, so these are generally the area where tsunamis are formed. You get your earthquake, your tsunami rolls. It could roll across an entire ocean, in which case you would have hours to evacuate, or it could form right offshore, in which case you would have no time to evacuate. And that's where the loss of life occurs, because these deep ocean earthquakes right on these trench regions, one part is usually close to land, you get your huge tsunami. The other part, far away, you don't have much loss of life, you take some property damage. Island arcs, we'll focus on the island arc, not just Japan, Caribbean, everything like that. They form with the uplift of ocean to ocean collision. Ocean to ocean collision, you have uplift. These are basaltic islands, not granitic or like you have on the continental. They don't explode, they grow into shield volcanoes. This is typical of Hawaii, Caribbean, Aleutian Islands, the Philippines. So ocean to ocean subduction, island arcs forms archipelagos, is another term for it, archipelagos or island arcs. Our explosive type volcanoes, like the Andes, the highest here, are ocean to continent. The unique continent to continent exists in the Himalayas. You can see you have the highest mountain range and these high plateaus surrounding it, high mountain range. Here is the fault right here. Both sides are being uplifted in this case because they're both rising. Now you have your downpour here. These are still growing, the Himalayas. So every person who reaches the top of Everest has climbed the highest mountain, tallest mountain in existence. Hawaii is a higher mountain if you measure from the ocean floor, from its origins. But every new person becomes the all-time champ for mountain climbing. Now your transform boundaries are when they slide by each other. The most famous transform boundary is the San Andreas Fault in California. This I want to show you here is what we call a right lateral fault, because if you stand here, the plate's moving to the right. If you stand here, the plate's moving to the right. If the plates are moving in the opposite direction, which is possible, it would be a left lateral fault. So faults are given the right or left hand based on your observation of the plate you're facing. So when you look at the ocean floor, you have all three types of faults. Convergent is called destructive because it destroys lithosphere, that melts. It has trenches, you have coastal or archipelago active volcanoes. Your constructive boundary, constructing new crust, is your divergent. Those are oceanic ridge systems. Also, you have divergence in Africa right now in the East Africa Rift Valley. You also have convergence on land, which is rare, but that's the Himalayas. And lastly, you have transform boundaries due to plates sliding by each other. Mantle plumes or hotspots are upwelling areas that are, it's called intraplate tectonics, in the plate. So here is your hotspot in Hawaii. There's Kilauea. That's the most active volcano right now. Mauna Loa is the largest volcano. So there's 3 shield volcanoes here on the Big Island, and then a 4th, which is almost to the surface. So the Big Island is growing, but it's also moving. When it moves over this hotspot, it becomes extinct volcanoes, littler islands, as they erode down. And then finally, seamounts, extinct underwater volcanoes. The weight of them causes it to sink, and they become deeper and deeper as you move away from that mantle plume. Because remember, the crust is floating on the mantle. So if it's not growing, that weight is kind of causing isostatic sinking or subsidence. It sinks a little bit. So here's some of the hot spots in the world. We have ones in the middle of the plate. They don't tend to be dangerous out to sea. I mean, you can get earthquake activity, but they don't tend to be as dangerous. You tend to have volcanic islands. When they're on land, they tend to be pretty bad because they explode. Here's your East African Rift Valley. Oh, this is where Africa is being pushed toward Europe, and that Mediterranean Sea is closing. You also have mountains like Etna, which in Sicily, which explodes. So we do have plate tectonics occurring there. There's your Himalaya subduction right there. So this is a hotspot area. Iceland's a hotspot. Here's some intraplate right on continents, but really much more common at plate margins and in the ocean. Of course, 70% of our planet's covered with ocean, so it stands to reason that the prominent hotspots would be oceanic as well. Wilson put together what we call the Wilson cycle. So he named it after himself, and I would too. I imagine I'd call it the nickel cycle if I had discovered it. This is the life cycle of a fault. Granted, he's using time lapse to discuss it, looking at all the different places on the planet, radioactive dating, how old it is, and trying to order this whole plate tectonic cycle. The first part of the cycle, and we've discussed every part of the cycle now, is your embryonic. You start off with your warping, then your Rift Valley, and eventually that Rift Valley will start to fill with water. So embryonic, like the East African Rift Valley, when it gets a little more mature, you have a juvenile. So you went from embryonic to juvenile. The example he uses is the Red Sea. You have the narrow sea. You're forming that ocean ridge. It's a baby. You're starting to get deposition. So it's not quite an ocean, but it's taking on the features of the ocean. So you went from warping to Rift Valley to juvenile to mature. Now you have divergence is the main motion. you have your oceanic ridge, you have your deep ocean floor. Notice here now you have deep ocean floor, abyss. You have continental shelves. You don't have coastal plate tectonics yet because it's not fully mature. It's maturing. Eventually, the cycle turns on itself and you're in decline. And now notice you have your continental margins with trenches, coastal volcanoes, no more mid-ocean ridge because you're shrinking, more like the Pacific Ocean. You have a lot of island arcs or coastal volcanoes around trenches, very narrow continental shelves. Eventually, you become terminal, kind of like the Mediterranean Sea, where the continents are really close together. You don't have much tidal flow. And then the continents come together. That's called suturing, continental to continental motion with uplift, like the Himalayas. Something that I will include in the review, like we looked at this, I happened to locate a quick Wilson cycle as well. So, and it does list and show you where in the world each of these are. Here's your embryonic Rift Valley, the juvenile Red Sea. Notice they're all connected. You have your terminal Mediterranean Sea, your sutured Himalayas, your mature Atlantic Ocean basin, and your declining Pacific Ocean basin. So I can throw this up on your quiz review as well, the stages of the Wilson cycle. So we measure plate motion using satellite technology so we can get it to the nearest millimeter. And the slowest is in the Arctic, where you have less than 2.5 centimeters per year. And the fastest motion is the Pacific rise, where it's more than 15 centimeters per year. So varying greatly. Mantle convection, like we mentioned, convection is how energy is transferred in a fluid, is what powers plate tectonics. Residual heat from Earth's formation, radioactive decay, basically drive the engine. Now, plate tectonics can be bad because you get the earthquakes and the volcanoes and the landslides and the tsunamis, very destructive. Here, this is a volcanic eruption in the Philippines called Mount Pinatubo. Pinatubo occurred in 1980, displaced millions of people. This hot ash plume can travel hundreds of kilometers per hour, and it is 400 or 500 degrees of hot ash. So it flattens forests and causes widespread destruction. This is a tsunami travel time. We measured 2 tsunamis here. You had an earthquake in Valdez. That's subduction. There's your Aleutian Islands. You do have your trench. And it radiates outward. And it took 6.5 hours to reach Hawaii. Or an earthquake in Chile, it took 14 hours to reach Hawaii. So the tsunami can give you plenty of time to evacuate, but the one that occurred here in Japan not too long ago gave Japan a minute to evacuate before it slammed into the coast because it occurred really close. So these tsunamis are very, very dangerous, very destructive, but it just depends on where you are on location. Now, all these Pacific Rim countries, spearheaded by America and Japan's technology, use satellites and have buoys, and these buoys are located all through earthquake zones. When there's an earthquake, the buoy gets the shift in pressure, contacts the satellite, and the satellite sends information to all of the major cities on the Pacific Rim, an alarm sound, and it takes approximately 7 minutes from an earthquake till the entire Pacific Rim has been notified. So it's fairly efficient. But there's some positives to plate tectonics as far as people go. This is an area where we have mantle upwelling. Now remember, density stratification separated the heavier elements from the lighter elements in Earth's, when Earth formed. So that upwelling brings those heavier elements back up. They tend to be metallic. Metals are very metals are very valuable to humans. So our mining is based on them. Our mining. They also provide fuel, geothermal energy, and very fertile soil comes from them. So you have volcanic eruption, which is destructive, but that volcanic soil is rich and very beneficial to agriculture. So that wraps up the plate tectonics lecture.
Can I ask a question?
Yeah, I can take a question right now. Shoot.
What's the difference as far as, for example, tsunamis between an earthquake and a volcano? Do they equal? Can they be equal, or is one
They
unique?
could be. A tsunami just means seismic sea wave. So
Yeah.
any seismic disturbance can cause a tsunami. An undersea volcano, an undersea landslide could cause a tsunami. Even a meteorite impact could cause a tsunami. So they're just, I mean, there would be a different source, but the same result.
Well, how common is one or another to produce tsunamis?
It just depends on whether if you're living in an active volcanic zone, volcanoes would cause tsunamis. If you're in an area where you have the subduction, then you would have more earthquake. So it's not one or the other, it just depends on your location.
Thank you.
Oh, you're more than welcome. Now, this week, we do know what's due. This Wednesday, we have the current events due and your module quiz. So make sure you work on that. This unit you have that we're currently entering, the plate tectonics, the ocean floor, due next Wednesday. Today, I'm going to just talk about the discussion forum associated with it. And then Wednesday, I'll talk about the assignment associated with it. But I want to touch upon the discussion simply because the sooner you post, the better chance students have to read your post and write responses. I want to compliment the class as a whole. Your first discussion forum was fantastic. Most of you wrote 2 beautiful paragraphs. Your responses were very good. Most of you wrote a full paragraph response, very thoughtful. I wanted to just encourage you guys to keep up the good work. You guys blew the earth science guys out of the water. I'll tell you right now, you guys are definitely winning 1-0 as far as quality and effort that I saw. So that's a big thumbs up to the oceanography crew. You guys were superior in every way. So keep that up and I'll make fun of them and tell them how great you are. But this time we do have a TED Talk and this one's really cool. The guy's a really good speaker and he's talking, his name's Dave Gallo, and he's talking about the deep ocean. It does include some plate tectonics and it includes a whole bunch of cool sea life that, you know, we're moving into our unit, the ocean floor. So this is a great video to watch and learn a little bit about plate movement and a little bit about that deep ocean floor and how chemosynthesis powers the ecosystem, not photosynthesis. So give this Deep Ocean Mysteries a watch. It's discussion forum number 2. It's located exactly in the portion of the class. I'll run to the class again. Where are we? Here we go. It's again located where you can click on the content. And in module weeks 1 through 8, the midterm, we have our weekly activities, and discussion 2 is located in week 3 because we are in week 3. And there's your discussion forum with the link to the program. If the link is ever down, all you really need to do is Google the guy's name and write TED Talks, and it'll come up. Everything's on YouTube. People have YouTube this and all that. So it's really easy. If there's a one way, there's workarounds every way to go. But that concludes our lesson for today. I would like you to spend the next rest of the day, rest of the time working on the current events that's due on Wednesday and studying for your quiz. Any other questions before I turn you guys loose on the world?
Yeah, when is the quiz review going to be published?
It should be, it was part of our, where are we? It was part of the Zoom list. And if you, so it's in the Zoom videos. And if you go to midterm modules and you go to quiz 1, you can see the review is there for quiz 1.
When is quiz 2 review?
Well, I haven't put it together yet because quiz 2 is not current. We haven't finished unit 2 yet. So it'll be available when we finish unit 2.
Thank you. And what's the name of the TED speaker?
Dave Gallo.
Thank you.
You're welcome. All right. Well, everyone have a great day.
Oh, I have questions.
Oh, well, please ask.
Maria,
Yep.
I want to ask about this water project. I watched the videos, a very nice video you did create, and what is we have to do?
I don't know what you're asking. I'm sorry.
About the project,
Which assignment are you referring to?
extra credit.
Oh, extra credit. There are a slew of videos that you're watching, and then there's instructions on how to file the extra credit report.
Oh, okay. I didn't.
So
see.
when you go to the extra credit module here, you can see here is the videos that you watched. This is all the videos from your field trip.
Yes.
Then here are the
I don't think you're sharing your screen.
Oh yeah, I should share the screen. Thank you for telling me that. Where are we? There we go. Share. All right, let's share the screen. I'm in the extra credit module right now. You can see along the side where you have extra credit module. And when you click on that, you get this Fort DeSoto extra credit, and then there's where you submit it. You open it up, here are all the videos from the field trip. Notice I have a winter trip and a summer trip.
I might be having issues, but I'm still not seeing your screen.
It didn't show.
See it now?
Yeah,
Yes.
thank you.
All right. Wow, just extra buttons to click. All right, here we are again, down the side, extra credit module. Third time's the charm. We can open it up. Here are all the videos. So these are all video shorts on site, different parts of Fort DeSoto. Here's the instructions on how to write it up. Okay, little background on barrier islands. We're going to cover barrier islands. So we're kind of getting a little ahead of ourselves when we cover, as we go through the class, we're going to learn more. So it'll be a lot easier as the class goes on and your knowledge base builds up. Watch the videos. When you submit your report, cover, location description. Now, there's two distinct sets of videos, the summer and winter. So you're going to put summer conditions and winter conditions. I'll mention tides, biotic factors that you see in the videos. Make a species list of all the organisms discussed. Phylum or division. We're learning those. We haven't learned those yet. That's why I said as we move along, you're going to learn the kingdoms, the phylums, and divisions. And then the habitat we found it in. Answer these questions, which I discuss in the videos, in full sentences. This is an addendum, an appendix. Again, we're covering this in class. We have not covered this yet. This is part of our marine biology unit. We're only in 1 or 2 right now. Again, we're covering this in class. So a lot of this extra credit, here's where it's located and where all the videos are, but you're going to have to learn more before you complete it, because we just are in week 3 of the class. We just haven't got far enough to cover it all yet. Okay?
Yes. Okay, thank you.
Okay. So this, you really, after the midterm, when you have a little more information, and then when we're in the marine biology unit, you'll have the knowledge base to actually complete the kingdoms and that stuff. Anything else?
Yeah, and I have one more question. With midterm exam, is it an honor lock exam?
Yes, it's an honor lock exam, yes.
Honor lock.
And you want to wait till we've covered all the material before the midterm, before you take it.
Yeah, sure. Yes.
You don't want to take it now because we just have.
No.
All righty, everybody, have a great day. Thank you for coming.
I had one unrelated question.
Awesome, shoot.
All right, so when I was looking through chapter 2 or 1, I think, I saw that they mentioned that a decrease in atmospheric oxygen was linked to all of the major extinctions. Now, so I saw on the graph that there was a decrease in atmospheric oxygen before the most recent extinction of the dinosaurs. Now, I did some research and I found one paper from 1993 that said a meteor wasn't the cause of the downfall for the dinosaurs, and that it was actually a decrease in atmospheric oxygen. And I was wondering, since that was so old, if that has been disproven since then, or?
It's, I mean, disproven, again,
Well, yeah, you can't disprove it.
So that's not really most of the evidence points toward the meteor impact and not the oxygen. Also, you could say that the meteor had impact because it hit and split the mantle, or allowed the mantle to come up. Kind of when it hits, it makes that crater and outgasses. That our oxygen content changed. There was more carbon dioxide, water vapor, and dust in the air, lowering the oxygen content. So the event caused less oxygen as well.
I see. So the meteor would have hit before.
Well, the meteor hit, when it hit, it shot dust and blocked out the sun for quite some time, ending photosynthesis, which creates oxygen. Also, a lot of gases escape from, if you burst a balloon, the gas escapes out. So we have gases in us, in our mantle, that would have escaped out, changing the methane and carbon dioxide content of the atmosphere as well. So photosynthesis stopping, and that would have led to a decrease in oxygen almost immediately.
Okay, I might be reading too far into the graph, but it just looked like the oxygen decreased before the extinction, like a couple.
Yeah, I haven't read that paper, so I can only comment on, I know that the oxygen content dropped immediately when things happen because of the dust, because of the lack of photosynthesis, and because of the gassing, the increased volcanic activity. But it's also been discussed that there was an increase in volcanic activity before the meteorite hit as well. So the dinosaurs were dwindling and vulnerable.
I see. Okay, thank you.
So that's also been, that's also out there. So they really haven't disproven the lack of oxygen more than they've proven that there was an impact that was catastrophic.
Okay.
Okay?
All right, thanks.
Oh, you're more than welcome. Well, everybody, have a great day.
Have a good one.
Yep. Bye.